All right. Chapter 15, dilutions. When, so far with all these modules we've been going through with proportions and such, it's a little different with dilutions. With dilutions going from a stock to a diluted, for diluted to a more concentrated solution, you want to make sure that the amount of moles remains constant. And that's why we want to use the equation C1 V1 equals C2 V2. You probably have seen it as M1 V1 equals M2 V2 because the molar concentration times the volume of that solution equals the amount of moles of that solution. And so the amount of moles for one solution should equal the amount of moles in the diluted solution. That's what the whole idea is. So with proportions, you can't exactly arrange that. It comes out as a different number. So that's why we specifically use this form of equation, just because we want to preserve the preservation of the amount of moles. So let's get right into that. Um, we use C1V1 because, yes, we are preserving amount of moles and such, but we can, concentration can be written in various forms. And so we don't have to take the time of like elaborating and turning it into moles. We can just, as long as it's, one form of concentration that is the same as the other form, another form, as long as it's the same form of concentration on both sides, then we're fine. So we can just rewrite it as C1V1. Let's start with number one. It's case in point. If 250 milliliters of a 1 to 800 volume to volume solution were diluted to 1000 milliliters, what would be the ratio strength, V to V? Okay, so using that equation, we don't have to convert 1 to 800 into grams and then from that into moles and such. We can leave it as, if you want, 1 over 800. So that's what it is in fraction form. And then that's 250 mLs of that. That should equal um, some sort of concentration times in a 1 liter solution. Okay, it's pretty simple setup, right? So we get to our calculator here. We can do 1 divided by 800 times 250 divided by 1000. So that's what our answer is, um, as its fully divided form. So fully divided form. We need to find the ratio strength. So that's basically looking at something like this, same thing. So how do we go about that? We just divide that, so under 1. So 1 over under, yeah, 1 over 0.000325. You do 1 divided by this, 3,200. And then that is our ratio, 1 to 3,200 volume to volume equals C2. Pretty straightforward. This is Gen Chem all over again. That rhymes. Not really. Anyways. Similar idea, just, extra work into getting that goal. Number 10 is our next problem. It is a homework problem. How many milliliters of a syrup containing 85% weight to volume of sucrose should be mixed with 150 mLs of a syrup containing 60% weight to volume of sucrose to make a syrup containing 80% weight to volume of sucrose? A lot of sucrose going on here. Just let's take a moment, close your eyes, breathe. Okay, so you have the percentage of one with a certain volume. You're adding another volume of a different percentage equal a percentage with the combined volumes. How would you see that as, just writing that out as variables possibly, right? So open your eyes now. You would say, let's just write A as a concentration, okay? Times a volume. That was our first, that's what we said earlier. We're adding a volume of another concentration, and that will equal a total uh, concentration with both volumes being added to it. That is the setup of this problem. So that's the general structure of it. All we have to do is fill in uh, the appropriate variables to their appropriate numbers, right? So we can do 85% of x, 85x plus 150 ml of 60% equals 80 of x plus 150. We already know what y is. Y is 150. So we could just put that right into the, whoa. Okay. So let's expand, get, see if we can make this look a lot nicer. 85x stays the same. 60 times 150, that's 9,000. 60 times 150, yes. 9,000 equals 80x plus 15 times 8, 60, the 1,200? No, 12,000. 80 times 15. Yeah, but it's 150. 80 times 150, 12,000. Okay. So we've expanded. Let's isolate things. So isolating 80x, 85x minus 80x, 5x equals 3,000. X equals 600. 600 mLs. So, I mean, it seems hard at the beginning just because like it's something that you need to think a little abstract for. But when you see it, when you close your eyes and take a chance to like see it out, it's not as bad as it looks, right? But maybe memorize it for the exam. So when do you use that specific scenario formula for that scenario, right? It's you have the strengths of all components, but you don't have the volumes of all, right? So they could have given you of the final volume and the final percentage along with the other percentages, but no volume for either one. And then so then when you isolate that, you have X and a Y. That gets into a lot more work. But we get the idea for this. Okay, 11. Okay, number 11. How many milliliters of 28% weight-to-weight strong ammonia solution having a specific gravity of 0.89 should be used in preparing 2,000 mLs of a 10% weight-to-weight ammonia solution with a specific gravity of 0.96? So a lot of previous concepts in this question, but we can handle it. We can go through it. Let's just start out with our pyramid. Now, one thing to mention here before we go ahead with this is that I write I write I write H2O just out of simplicity, but it really is just grams of substance over the equal amount of solvent, and that could be any. It depends. Your density would be involved in that as well, but just knowing that generally it's the grams of a substance over the solvent of equal weight or equal volume, weight of a equal volume of a solvent. That's the whole idea of specific gravity. Most cases it is H2O. That's why I write it as H2O. But for this example, for like it doesn't really state, right? So we just go by solution. All right. So we're looking at these and we're given mLs, but the percentages in weight to weight. So that's why we need the specific gravity. Got it? So there is 2,000 ml of solution, okay? And we want to get that as grams. So what do? We multiply that by the specific gravity. So 0.89, sorry, 0.96. Okay. 2,000 times 2,000 times 0.96. It's 1920. 1920 grams. Okay. And so now we're looking at this question and they're asking how many milliliters for a stronger weight to weight was it solution? Yeah. So with that 10%, we can redo our C1Q1, C1V1 equals C2V2. So that's what, 10%, 1920 grams equals 28% of V2, but V2, right? So V2 equals, let's find out. It's 1920 times 10 divided by 28. 685.71 grams. They're asking for milliliters from that, so we have to, of the solution. So we given that grams, we had to divide by the specific gravity right now. So we divide by the specific gravity for this solution, which is 0.89. We get 770.47 mLs of 28% weight-to-weight strong ammonia solution. All right, that is it for chapter 15. I'll see you guys at the next video. Peace.